Hello, everybody. Now we come to this topic of continuity, continuity of a function at a point and also on an interval, perhaps on its entire domain, right? Continuity, this is a concept which is very, very important from the standpoint of calculus and mathematical analysis, closely related to the study of limits. So let's look at the topic of continuity in section 2.4. All right, section 2.4 is on continuity. All right, you may want to jot down or try to sketch these 5 functions because each of these is going to represent something a little different. And I'd like to point out a few things about these 5 functions. Okay, so you see F1, that seems to be, straightforward, smooth line. F2 has a hole at A, comma 2. And then F3 has a hole also at F, comma 2. But the function is defined at A, which is, the value of F3 at A is 3, indicated by this black circle right here. And then F4 has a discontinuity, which is, by the way, a term that we are about to define, in the sense that there is a jump at A. The function jumps 3 down to 2 and then continues to go on. And then F5, of course, has a vertical asymptote. All right, so let's look at these a little more carefully. All right, so we have a function, which is F1, F2, F3, or whatever. Right, and then is the value of the function there? Is function defined at A? If so, what is the value? And so on. And then the limit of f of x as x approaches A. Okay, so we are going to look at these things for each of the 5 functions, F1, F2, F3, F4, and F5, of course. All right, that doesn't, oops. Some strange things happen sometimes. Okay, so we have these 5 functions. Okay, so first, what is f of A? What is f1 of A? Well, that looks like it's 2, right? That's easy to find. And then what's the limit of the function right at this point? Well, if it's, there's no gap and the value of the function is where the f of x approaches as x approaches A from the right and from the left. So f of, or the limit at A appears to be 2 for the function f1. How about f2? Now, f2 is not defined at A. So this is undefined or does not exist. It's basically the same thing. When you say undefined, it means it does not exist. And then for that point, what is this? It's the limit is, well, remember the limit doesn't care what happens when x is precisely at A. As x gets closer and closer to A from the left or from the right, the value of the function f2 still approaches 2 infinitesimally closely. So the answer is 2. F3, now we have f3 is defined at A, and that value, as you can see with this point, is 3. So the value of the function, whoops, what happened here? The value of the function, I should undo here. Something is happening. There, okay. The value of the function is, this is f3 of A, is 3, even though the limit is 2. Okay, I hope you can see that. As x approaches A from this side, the value of the function approaches 2. It never becomes 2. In fact, it jumps to 3. And as x approaches A from the right, the value of the function still approaches 2, even though it jumps to 3 when x is precisely at A, right? So the values, the value of the limit is the same for all 3 functions. For f4, you know what f4 of A is? It's not this open circle, but it's a closed circle. So the answer is 3. Now the limit, you can easily tell does not exist, right? Because the limit from the right is 2, limit from the left is 3. And so the limit itself does not exist. And then f5 is, well, f of A does not exist. And if you look at the limit, I mean, you can say it does not exist, but more specifically, the limit of f5 as x approaches a from both sides is positive infinity, which is not a real number, as I said many times. Okay, so every one of these has a different behavior at the point A. Now, of all of these, which one do you think I would say is continuous? Or which one do you think is continuous? What is continuity anyway, right? What you wanted to say is like, okay, if it's continuous, it shouldn't have a hole. Maybe you learned continuity as being able to draw, you know, on one stroke of a pen or pencil without lifting the pen or pencil. So if you have to go like this or go like that, you know, it's not continuous. And that's a good description, not very mathematical, but it's a good description. So what you want to say is, if you look at F2, it has a hole, F3 has a hole and a point away, F4 has a gap, F5 goes to infinity. So it looks like F1 is the only one that is continuous at this one particular point A, right? Is that right? Well, that depends on the definition, of course. And so now I'm going to give you the definition. By the way, this is a correct statement. All right, so here's the definition of a continuity. Remember, in mathematics, definitions are very important, especially as you study calculus and beyond. Definitions are going to become super, super important. All right, so F, we say a function F is continuous. Here's a word I'm trying to define. And we want to talk about a pointwise continuity here. F is continuous at the point A, x is equal to A, if and only if three conditions are met. Number one, fx is defined at A. So that would exclude things like F2 and F5, because those are not defined at f of A. Yeah. All right, not defined at A. And then number two, the limit of f of x as x approaches A must exist. And so that would preclude or exclude F4, because F4 does not have a limit at that point. See, whenever there's a jump, as in F4, we don't want to say it's continuous. And then finally, these two are equal. The limit of fx as x approaches A, which by the way is, you know, what do you know? That exists by number two, right? Is equal to f of A, which is guaranteed to exist by this number one. So three things. Actually, if you skip these two things, if you just say the third one, limit is equal to the value of the function, that is all you need. Because if you say that, that assumes that this one exists and this one must exist, right? So this is really the defining relationship in for the continuity of function at the point A. Okay, so what did we just say? IE, that's an abbreviation for that is, okay, or in another word, or said other ways, basically it says f is continuous at A if and only if its limit at A is equal to f of A. The limit is equal to the value of the function. Easy enough, right? But you do want to remember this definition. This is probably the first time you formally defined the word continuity. All right. Later on, if you continue to study mathematics and when you study more advanced topics, you may come up with a better and even more general and abstract definition of continuity. That's okay. And in fact, some of these definitions are quite challenging to understand using terms like epsilon and delta. And there's even a higher level of continuity that you can study. So this idea of continuity turns out to be one of those core fundamental ideas of all of mathematics. But anyway, you can wait until you study more advanced definitions. At this point, this definition would be good for continuity of a point. Okay. So otherwise, that means else, if it's not continuous, then f is said to be what? Not continuous, okay? And the word is discontinuous. So discontinuous at A. So the function is either continuous or discontinuous at A. If this equation doesn't hold, or if one of these or both of the sides are missing, then we say the function is not continuous, or you can say the function is discontinuous at that point. Okay, so when is the function discontinuous? Types of discontinuity. Okay, let's talk about the types of discontinuity. I have already given you a bunch of behaviors where the function is discontinuous, right? Like if you have a hole, F2 has a hole right here, right? And F3, of course, has a hole and a point. F4 has a gap, and F5 has a vertical asymptote. It looks like these are the things you want to avoid, all right? A hole, a single hole, a gap, which could be called a jump. The problem, by the way, is, these are, you may have learned, okay, in an algebra class, that a function is continuous unless you have a hole, a gap, or a jump, or a vertical asymptote. And that's okay. Now, vertical asymptote can be defined well, but have you heard of a definition, a clear, precise mathematical definition of a hole, or a gap, or a jump? Okay. See, these are hard to describe in a precisely mathematical language. And that's why we stick to this idea of continuity using limits, all right? Because a hole, for instance, is a very hard one to define. All right, so these are the types of discontinuity. Now, if you have a hole, okay, if you have a single hole, you can actually fill in the hole with that value, which is the same as the limit where the missing hole is. Okay, so this one can easily be removed. So this is sometimes called the removable discontinuity, just by adding that point to fill the hole. Fill in the hole. The other discontinuities are harder to remove, and in fact, they are sort of impossible to make these continuous, right? So these are non-removable discontinuities. All right, so you can classify just by looking at the graph which one is a removable discontinuity, which one is the gap, and which one is the vertical asymptote. All right, so that's one thing. Now, the second thing that I want to define is this: f is continuous. And you say, wait a minute, didn't we just define that? Yes, we did. But this time it's not a pointwise continuity. F is continuous on, I didn't write on an interval. Typically, we talk about an open interval, AB, if f is, now this one's easy. See, this one is continuity over an interval, but it's an easy definition because f is continuous on an entire interval if and only if. Remember, if and only if is should be in all of the definitions in mathematics. F is continuous